SwayamPrabha. Digital India. Educated India.
Hello everyone, this is the last lecture of this week. In fact, this is the last lecture of this course. Today we will conclude the entire course, but before that let us complete the discussion that we started in the last class. Finite element method in three-dimensional problem. In the last class we had seen how it is to be implemented for a scalar value problem, specifically for a heat conduction problem, and we will see what are the equations for linear elasticity problem. I repeat, as I said in the last class also, as far as three-dimensional problems are concerned and finite element implementation in three-dimensional problems are concerned, our discussion will not be very detailed. We had a very detailed and in-depth discussion on various aspects of finite element method in one-dimensional and two-dimensional problems. What we have been doing in case of three-dimensional problem is just extending the similar concept in three dimension. So if you recall, if we have to apply finite element method in for a linear elasticity problem in three dimension, but if you recall, this is the element equation for plane elasticity. Plane elasticity means it is either plane stress problem, plane strain problem. It is in a two-dimensional problem. Governing equation is similar. This is the stiffness term, this is the degrees of freedom, and this gives you the body force term, and QE is the traction term, boundary traction term. Stiffness matrix is obtained like this, where T is the thickness and then C is the constitutive relation. For plane stress, the constitutive relation is this. For plane strain, the constitutive relation is this. Mu is the Poisson's ratio and E is the Young's modulus. And B matrix is this. It essentially gives, it is the derivative of the shape function. Okay. And and then the body force term and the boundary traction term are written as this. Now, since for plane elasticity problem, we had seen at every node we had 2 degrees of freedom, displacement in x direction, displacement in y direction. So therefore, our stiffness matrix here will be 2n by 2n, where n is the number of nodes in the element. And body force term has a 2 component, fx and fy. Similarly, the traction term has 2 component, tx and ty. Now, when we apply to this 3 dimension, the equations will remain similar, but only thing is because of additional dimensions, there will be some more information need to be in these matrices. For a 3-dimensional problem, the constitutive matrix will be this. This will be a 6 by 6 matrix. We have 6 stress and strain components. So this is the constitutive matrix. And if we have we have seen various different kinds of element in 3 dimensions. These are the very popular elements. So at every node we have, suppose this is node number 1, 2, 3 and 4, and then we have 3 degrees of freedom like this, and then this. Okay, these are all 3 degrees of freedom at every node. So if you have a quadrilateral element, if you have a tetrahedral element, so then our size of the stiffness matrix will be 12 by 12. 12 by 12. Similarly, if it is a brick element, then for brick element we have 8 node, and then size of the stiffness matrix will be, this is another node, and this is how the node numbering we have given, 1, 2, 3, 4, and then 5, 6, 7, 8, and every node similarly we have 3 degrees of freedom like this, and total stiffness matrix, size of the stiffness matrix in this case will be 24 by 24. So yes, like this. These are all local degrees of, this is degrees of freedom. Now, so for this element, what would be the corresponding? So we know that this is the C matrix. So once we have C matrix here, if we know the B matrix, then we know the expression for stiffness matrix. So the expression for B matrix will be this, the T will be there. Okay. So expression of stiffness matrix will be, this is for say node number 1, 2, 3, 4. This is for node number 1. Okay. Similarly, the entire block will be repeated. This block will be repeated. If it is tetrahedral element, we have 4 nodes. So this entire block will be repeated 4 times. So next will be del phi 2, del x, then 0, 0, then 0, del phi 2, del y, 0, then 0, del phi, 0, this is 0, del phi 2, del z. Then similarly here will be del phi 2 del y and del phi 2 del x, 0, then 0 del phi 2 del z, del phi 2 del y. These correspond to strain component. 1 is 2 z, then 0 del phi 2 x, right? This is for node number, this is for node number 1, this is for node number 2. Similarly, we can have for node number 3, and then we can have node number 4. This will be del phi 3 del x, 0, 0, del phi 0, del phi 3 del y, 0, and so on. If you have a, so this matrix will be 12. So this matrix will be 6 by 12 matrix for tetrahedral element. Now, if we have brick element, similarly this matrix will be 6 by 24 elements. So once we have this B matrix, we already seen the C matrix, then we know the expression for stiffness matrix once with respect as a function of x and y. Now this integration needs to be performed using Gauss quadrature technique, and we have already seen how to perform this integration in Gauss quadrature technique in three-dimensional domain. Now once we have this stiffness matrix and then traction vector and then body force term, and then finally the element equation KUE is equal to FE plus QE. This is the element level equation, and then this, if for every element we have such equations, and then all these equations need to be assembled, and assembling concept of assembling is exactly same. It all depends on how the elements are connected. Based on the connectivity, the stiffness matrices, element level stiffness matrices need to be assembled to get the global stiffness matrix. Once we have the global stiffness matrix, then at every node we need to impose the boundary conditions, essential boundary conditions on the nodes where essential boundary conditions is prescribed, and that step is also exactly same. And once we impose the essential boundary condition, we partition the matrix based on known and unknown information, get the condensed equations, and once we get the condensed equations, solve it for unknown displacement first, and once we have solved for unknown displacement with the knowledge of once the unknown displacements are computed, and then if the another condensed equation to get the unknown forces, and then we can do the post-processing and all these things. So next, the step is exactly same. We had a discussion in case of two-dimension problem. I am also not going to show you any in one-dimension, two-dimension problem. After first we did some manual calculation, and then entire concept was translated into a code, and through that program we could take large number of elements and then see the convergence. We are not going to do the same exercise here in case of three-dimension problem. I leave it to you. If you face any difficulty in translating this into a computer code or understanding any steps in three-dimension problems, you can write in the forum. We can have discussion there. Okay, so this is how the finite element method can be applied to three-dimensional problem. Now let us with this let us conclude the entire course. Now I would like to take you to the very first lecture where we discussed or introduced finite element method as a technique for determining approximate solution of partial differential equation describing or representing various physical processes, right? So now sometime what happened, these equations, getting solution of this equation for the entire domain is difficult, or sometime we may not be having a single equation for the entire system. So in that case, what the idea is to break the system into small subsystems, such that for every subsystem we can write the equation, and once we write the equations, once we have the information about the every subsystem, then assemble all this information together to get the equations for the entire system and then solve it. This is the premise, the basic philosophy of finite element method. And similar thing, if you recall, it was again discussed in the very first week. Similar thing we do in case of direct stiffness method as well. But in that case, the stiffness matrices obtained directly from the basic mechanics, right? Now, but then finite element method is a more general version of that, and it has an application in almost all branches in engineering and science. There are two important aspects that we try to discuss in this course. One is the theoretical aspects. It is very important to understand the premise of finite element method, the theoretical basis of finite element method. But then only understanding or only knowing the theory of finite element method is not enough. Eventually we need to solve real life problems. Eventually we need to analyze structure. Eventually we need to design the engineer. We need to find the solution of engineering problem. So with the knowledge of theory, it is also very important to know how this theory can be translated, and then how the implementation aspects, right? So we try to make a balance between the discussion on theory and the implementation aspects in this course. Now, another important aspect of finite element method is its mathematical basis. You see, finite element method has a very sound and beautiful mathematical basis, but that discussion on that was beyond the scope of this course. We did see some the expression of error, expression of different measures of error, but we had at that time we had taken those expressions for granted. But what is the premise of those expressions? What is the how those expressions are derived? Those discussions we did not have. So it is a separate course altogether, the mathematical aspects of finite element method. And with this background, with this platform on finite element method, I am sure that you will be able to explore that aspect of FEM as well. Now, finally, before we close, there is just for the completeness of the discussion. You see, finite element method has whatever finite element method we have seen, we can see today it has evolved over many decades, right? Now, there is another class of method, alternative to finite element. I won't say the alternative to finite element method, but it was started as an alternative to finite element method for a certain class of problem, and that class of method is called element free method. As you know, finite element method and the another class of method is element free method, where the steps are almost similar except one. In finite element method, we discretize the entire domain into a collection of elements, but in element free method, there is no elements. The entire system is discretized by a set of points, set of nodes. So from the finite element discretization, if you remove the element, you are left with some set of points. That is the discretization used in element free method, or also known as particle based method. And then these particles will interact with each other, the way here elements are interacting with each other, and how to establish that interaction. And then once that when we establish interaction in certain way, what are the consequences and implementation, that is a different discussion for that method. But just for the completeness, just for your knowledge, that there is another class of method which is called element free method. One example, if I give you, all of you, I'm sure, must be aware of finite difference method. A finite difference method is one example of that element free method. Like there are many other methods like element free Galerkin method. There are methods like smooth particle hydrodynamics. There are methods recently. There are methods called peridynamics. So those methods are still not a standard tool for analyzing different engineering problems, unlike finite element method, but those methods are developed or being developed, or people are working on this method, keeping application in a certain class of problem where finite element method, whatever in its form that we have discussed in this course, either has difficulty or certain computational issues, computational pitfalls we have to apply FEM as it is in those class of method. But there are another different versions of finite element method to deal with all those class of problems which was initially thought of difficult to handle using finite element method. One example is like extended finite element method, or very popularly known as XFEM, which is developed to model arbitrary evolving cracks in solids. Now, so this is just whatever we have discussed in this course is a small, it's like a tip of an iceberg. There are so many things we have in the basket, and definitely with this background, I am sure you will be able to explore the entire baskets and then see where do we stand in terms of computational mechanics as a whole. So with this, let us stop here and then all the best. Thank you.